Welcome everyone to my course CBS VLSI Design. In today's class, we are going to learn about high level synthesis of loops. So, as you know, this high level synthesis is a process of converting a C code into equivalent RTL code. So, in the C code, one of the important construct is loop, right, and in this class we try to understand how this loop will be effectively mapped into hardware. And since loop is something is iterative and its efficient executions is very important, otherwise it might has hindered the performance. Okay. So, the loops are actually implemented in the hardware in 4 different ways. One is the rolled implementation or the iterative executions, and then partial unrolling, full complete loop unrolling, and loop pipelining. In today's class, we are going to discuss about this rolled implementation, partial loop unrolling and full unrolling, and in the next class we are going to discuss in detail about the loop pipelining. Okay. Before going into the discussion, I am going to introduce certain terms which is important in the context of these loops and their execution in hardware. The first term is called initiation interval. Okay. So, the initiation interval says that how number of cycles between starting of 2 consecutive iterations, right. So, in the loop there are multiple iterations, right. So, the II or initiation interval says that how frequent the iteration starts, okay. And latency is says the number of cycles needed to process one set of inputs. This is the number of clock cycle once you give an input, what are the number of cycles you need to get the corresponding output. Okay. So, that is called latency, and then the another important term is called throughput. Throughput is there is the number of cycles between 2 outputs, right. So, you are getting output 1 corresponding to input set 1 and you are getting output 2 corresponding to input set 2. So, what is the time difference between these 2 outputs? Remember, this latency may and this throughput is always not the same, because latency is something, say you are giving some input and it needs a 10 cycles to get an output. So, the latency of the design is kind of 10 cycle, but your throughput can be 1, because if you design the circuit as a pipeline mode, then what is going to happen that your whenever your first output come, in the next clock your second output might come, if it is a optimal pipelining, right. So, your throughput will be 1, although your latency is 10. Okay. And initiation interval also not always same as latency, because it depends on how you are going to execute the design. Okay. So, let me take 2 examples to explain these 2 terms in more detail. Say you take the left hand side example where I am actually having a pipeline execution of the loop body. Okay. So, what is happening, say suppose that as the example I have given, that you say that if you give an input, you need 10 cycle to get the output. Okay. To process the input, to obtain the output, you need 10 cycles. Okay. So, you are giving the input 1 here and you are getting your first output here. Okay. So, that is the latency 10. You are giving your input here and you are getting your output, again it is 10 cycle, right. So, distance between the first input to first output, second input to second output is 10 cycles. So, the latency of this design is 10 cycle. So, what is the initiation interval? Because you are giving the inputs in every cycle, because it is a pipeline executions. So, the initiation interval or task interval is 1. Okay. And also you can see the difference between the output to output is also 1, so throughput is also 1 for this design. So, this is the pipeline execution of the loop, right. Now, you think about the iterative iteration of the loop. So, you are giving the first input here and you are getting your first output here, and say you need some time to read and all. So, total latency is 13 cycles. Okay. And after 13 cycle you are giving the second input and you are getting the output again. So, again the latency is 13 cycle. And what is the initiation interval? It is basically 13, because you are giving input here and then you are giving input after 13 cycle, right. So, here initiation interval is 1, here initiation interval is also is 13. Okay. And the throughput is also 13 in this case, because you are getting throughput every 13th cycle, right, not in every cycle. Okay. So, let us take another example. So, suppose this is the loop body. Okay. So, this is the loop body and this is the schedule, you need 3 cycles to execute this. Okay. And assume these are all array basically, some data which is basically available, right. So, now what is the if you execute in a iterative manner, iterative execution. So, what is going to happen? So, you give one set of data at clock 1, right, clock 1, and your output will come, so 1, 2, 3. So, after third clock cycle only your clock 4 you are going to get the first output at the start of clock, if you assume there is a register here, right. So, otherwise you can assume that it is after third clock is available, let us say there is no register. Okay. So, that means here and then after, so your latency of this design is 3, because there are 3 cycles, okay, to process the data. And since this design is not pipelined, so your initiation interval, that means you have to wait until these things are processed, you have to wait, and then only you can give your next set of input. Okay. So, then the II is also 3 and throughput is also 3, because every third cycle you are going to get the output. Now, suppose I make this design pipeline, right. So, I am adding this pipeline stages everywhere, then what is going to happen? So, now I can give input in every cycle, because this is stage 1 will process one set of data, this stage 2 will process another set of data, and stage 3 will process another set of data, right. So, for pipeline version, we have the initiation interval is also 1, and then latency is also latency is still 3, because for every set of data you need 3 cycle to get the output, but your throughput will be 1. Okay. So, this is how we calculate these values, and these are the important parameters in context of loop execution. Okay. Now, let us move to the first version of the loop, which is called rolled implementation or iterative implementation. So, this is the by default executions for loop. So, loop is basically have iterations, right. So, it is running for say n iterations, and one iteration there may be some 10 operations, right. And now you, based on your resource availability, you can schedule that particular loop body, and let us say that scheduling that loop body, one iterations of the loop take k cycle. So, that means you give one set of input, you run k cycle, one iteration is over, then you run the next cycle and so on. So, the overall time it will take is n into k, right. So, the overall time will be taken in this way is basically n into k, and it is the most simplest version of the loop, right. So, you have you schedule the loop body, whatever the, say it takes a 3 cycle to execute, and then you just loop it for n times, right. So, if n if I less than n you do this, and otherwise I less not n, then you go to the other part, right. So, this is how the controller FSM will be generated, and it will keep executing the loop for n into k minus cycles, and the rest of the things will wait until the loop completes its execution, right, because this is how I am going to execute the loop. Okay. So, this is how this is what the basic or the default implementation of the loop. Let us take example to understand better. Say I have this loop given where I am doing some accumulations of this d in, and since this d in is a small array, I am assuming this is flattened. Okay. These are actually put into registers. Okay. Now, what I am going to do? So, basically in every iteration what is happening? So, ACC equal to ACC plus d in I, right. So, I need one of addition operation, and that is the operation. So, the scheduling will take only one cycle, right, since I am assuming this array is split into registers. So, this particular for this adder, one input will be the accumulator, right. So, this accumulator is coming here like this. So, I have just put 0 in other way, because the accumulator initially should contain 0, and whenever the initially I can reset this accumulator with 0. So, I just choose a multiplexer to descend it. So, this is your basically accumulator, and the other input is basically d in, and now you have to choose this among d in 1 to d in 4. So, you need a mux, right. So, that will choose the appropriate value from d 1 to d in 4, and then this will send it here. So, this is my d in I basically, right, and this is calculation will be done, and it will put into the accumulator, right. And we have a counter I, which is basically will count from 0 to 3, right. So, whenever this I, so it will automatically increment from 0, 1, 2, 3. So, whenever it is basically become 4, it will automatically reset to 0, right. This is how this counter will work, and that particular counter, this direction should be in the reverse. So, this will be the selection of this data, right, because if it is I equal to 0, I am going to, if it is 1, I am going to select this and so on, right. So, this is how I can select the data based on this I value, and also this I less than 4 will be the write enable for this accumulator register. Accumulator is a register. So, till the time it is less than 4, I am going to write, after that I am going to stop. So, this is how I am going to execute the behavior in the hardware. Okay. And you can understand that this is basically a single loop operation, and it is basically looping here, right. So, for I less than 4, and once it is not, I will go to the rest of the thing, right. So, this is how I can actually store the when execute this, and it will need, since there are 4 operations. So, you need 4 cycles, right. So, you need 4 cycles to execute this. So, this is very simple, and it need minimum resource. The important factor here is that it need minimum resource, because you are taking only one iteration of the loop at a time, and you are actually assigning resource for that, right. But it takes lot of time, because it is take maximum possible time to execute the behavior, right. So, let us take another example where I can actually do some resource sharing. So, I will just show the execution of this part. So, since this is the big array and these arrays are big, so I cannot put them into, I should not split them into register, because it will consume lot of registers, right. So, I have now 4 arrays, array A, B, C and D, right. So, I should have that counter. So, I am writing some abstract design. So, this counter will decide the value address, right. So, this is the address, right. So, this is address basically. So, if I give this I, so it will just select AI, right, and there should be some write enable. So, I can actually just check whether I less than n or not. So, that will be my this enable signal. So, this is read enable, right. So, this should be so, I am going to say that this is basically a negation of this data. So, I will say that this is a read, you just read from this data, and then I will get this AI, BI, CI and DI here, right. So, this is how I should access this. I am assuming this arrays are mapped to block RAM. Okay. So, now I have all this data, and it will need one cycle, right, because these are all 4 parallel RAM. So, this is one, this will need one cycle, right, and then I want to schedule this. So, this scheduling can be, you can actually draw different kind of thing, right. So, basically it can be like this, right. So, you are doing say ACC A, then B, then C, then D, right. So, then if you try to do this, you need basically 4 cycle, right. So, you need 4 cycle, but you can actually do these things using a single adder, because it is a single addition operation, and you can actually multiplex the input, right. So, let me try to do that only. So, although there are 4 operations, I can actually execute in a single resource. So, let us say I have one adder. So, what is the input? So, I have the left input is basically is that accumulator. So, whatever the accumulator, so basically here this is accumulator I, right. So, I am updating the accumulator I, but what I can do is I can store this register in a temp register, right. So, I am going to store this register in a temp register, right. So, this is my temp register, and then I have a mux which will select between this accumulator or this temp, right. So, or actually I do not need this accumulator here. So, I can actually just select this temp, because initially this temp value, okay, I also need the accumulator, let us put it like this. So, this is abstract design, do not get much. So, there may be some minor bug, but it is okay, the basic idea I am just trying to convey. So, this is what is the mux, right. So, this is again controlled by this I, right. So, this I sorry, this is okay, this is basically not I, you should have a timer for this scheduler, right. So, there is a scheduler time. So, there is a S which is basically there is a counter S which is running from 1 to 4, because there are 4 cycle, right. So, that will be controlled by this schedule time. Okay. So, then what is happening here? So, and this I can also have some way you can control whether you take the SCCI or T, right. So, what is happening in the first clock, you read all those things. So, the read will be done in say first clock. In the next clock, you are actually performing this SCC plus AI, right. So, this marks will select SCCI and this will select AI, and that summation, this result will be stored in this T, right. And then in the next clock, this S will decide, and this basically this counter won't increase until. So, this is counter is basically S into I into S, right. So, this is not basically N into S, and you can actually do a mod here, right. So, just mod here mod S, because this I will increase once one execution is over. So, that so basically you can assume this counter is N into S, and this I will be, this is my I, which will can be obtained by just do a mod S, right. So, after every 4 cycle you increase I, right. This is how I am trying to mean this. So, next I will increase this S, and then now it will select this T here and this BI here, and then it will do this operation and store this result into T again, right. And then again the next clock, this T will come here and CI will come here, and it will do this operation, and you can do this. And then last cycle you can do this, and it will come here. In the next cycle, somehow you can actually use this S to put a enable here in some version of this, so that you write this data into SCI. This is the final value, right, or this is actually I am sorry, this is actually out I, right, and your SCCI is something another input basically, sorry. So, this is actually out I, because this is the output, and say SCCI is another array which will store like this, and then this will store in out I only, right. So, this is contain all zeros basically. So, this is a very abstract level design. So, this counter control things we have to accurately design, but the overall idea of this counter control thing is that I will increase only to I plus 1 once this one iteration is over, right, S is done, and then I can actually take I 2 and again I load it for 4 cycle. But the important factor is that although there are so many operations, and since I try to do this in say 4 cycle these operations, I can actually execute this things using a single adder, right. So, basically the objective of this discussion to emphasize that even if there are many operations and if I do a rolled implementation, my resource requirement is minimum. Okay. You can also take this diagram and actually try to draw this version of this dependency, right. So, you can actually do this, right. So, this is basically A I, B I, C I and D I, right. So, you do these things out here, and then basically you do this addition here. So, then this is done, and then you actually add with SCC, right. So, then you just do add with SCC. So, then in this version you need 3 cycle instead of 4 cycles. So, this is what is called tree height reduction. I reduce the height of the tree. So, since here there are 2 parallel operations, I need at least 2 adder, right. For this design I need only 1 adder, but here I need 2 adders because there are 2 operations running in parallel. So, based on your dependency, or you can actually modify the dependency based on your resource availability, and actually you can improve the performance. So, this will take you can understand if it is a 4 cycle 4 into n cycle, it is 3 into n cycle, right, and if you have 2 function units available, why not doing this, right. So, this is the idea. So, the key takeaway from this discussion is this loop rolled implementation of the loop is the basic way of implementing things. It takes maximum number of iterations, but it takes the minimum resource, okay. And based on your resource available, you can actually modify the dependency to improve the time requirement per iteration. So, I just modify this to this to reduce the time from 4 to 3, right. So, that was the idea. I will now move to the other extreme, right. So, this is the rolled implementation and I am going to talk about the full unrolled implementation, right. So, that means in the full unrolled version there is no loop, I am just removing the loop and I am writing the all iteration operations of all iteration together and I just completely remove the loop, right. So, then what will happen, it is basically become a basic block, right. It is a series of sequence of operations which is something is there. So, that is what is the another extreme end. So, you can understand here that in practice if there is no dependency between two iteration, this the iteration I and iteration I plus operations are in parallel, right. So, if I assume that one iteration take one cycle, so I can actually execute the complete loop body in single cycle, right. So, the earlier time it was n cycle, if I assume each iteration take one cycle, then it is n cycle, but here it is one cycle. So, it is a complete extreme end, but there I need only say one unit of resource, here you need a any unit of resource, because this all n iterations are running in parallel. Okay. So, this is the another extreme. So, usually you can actually do your unroll yourself or you can use the Pragma HLS unroll of Vivado just to do that. You just mention this within the loop, it will completely unroll the loop. So, the point here is that if you since you are completely unrolling, so it is actually improve the parallelization, because if the loop iteration there is no inter loop dependencies, the whole loop is basically running in parallel, right. So, if you have this resource allow, then all operation can be done perform in parallel, right, all iterations can be done in parallel, and in best case it can actually complete the whole loop in single cycle. If I assume that there is a operation chaining allowed and one iteration take one cycle to execute. Okay. So, let me take examples. So, suppose you have this loop, and one important point here is that for unroll you need to know the it should be static, right. So, unless you know this is fixed value, I cannot unroll the loop, right. So, that is the requirement, and then now you assume that there is this loop, right. So, now I suppose this is 4, right, and so then in the 4 iterations, if I unroll the loop content will look like there is a loop, the code will look like this: A0 equal to B0 plus C0, A1 equal to B1 plus C1, A2 equal to B2 plus C2, and A3 equal to B3 plus D3, right. So, there is no loop, I have this, and since there is no dependency between this, so I can actually add, I have say 4 adder operator and I can actually do this. So, this is A0 B0, I am just writing in short, A1 B1, this is A2 B2, this is A3 B3, and you will get this should be B and C, right. So, this is B0 C0, B1 C1, B2 C2, B3 C3, and this is A0, A1, A2, A3, right. So, this is what we can just do, and you can actually understand that I can actually do the things in single cycle. Okay. But your resource requirement is 4, right. So, if you try to execute this in a iterative manner, you need only one basically adder, and you need basically a mux which will basically, or basically you have a RAM, you basically give I, you will get BI, and you have a RAM which is storing say C and this is B, you give the address, you get CI, right, and you just add it, and this will be stored in A and you give the address I, right. So, this is the execution. So, this will take n cycle, so n say 4, so I will say this take 4 cycle, but one adder, right. So, the one adder here it is 1 cycle 4 adder, right. So, this one cycle is the extreme end, because I am assuming that there is no dependency between the inter iterations. But if there is a dependency between iterations, so you may not able to execute everything in single cycle. That next example highlight that, but try to understand that this although I get the maximum timing benefit, by my resource requirement also increase in the same factor, right. So, the performance increment in terms of timing or latency is same as the same factor of resource requirement. Okay. So, that is something obvious because you want to execute in parallel. So, now I take the second example or the first example that I have taken earlier, that you just do this accumulator D in, and if you unroll here you will get this, right. So, basically there is no loop, right. So, you just have there is no loop, it becomes a straight line of code. But here you can see that this iteration that because it is accumulator equal to accumulator plus D in. So, whatever I am calculating accumulator in I 0, I 1 will depend on that, right. So, it is basically you can see here this accumulator is getting used here, this accumulator is getting used here, this accumulator getting used here, right. So, as a result, so there is a inter iteration dependencies. So, I cannot execute this if you want to execute. So, the dependency looks like this, right. So, you have this, but this is your accumulator. So, there is a dependencies. So, in general I have to schedule in 4 cycle, right, because if I assume there is that operation chaining is not allowed, then you have to execute in 4 cycle. So, your although you unroll, you do not get any benefit in this case, right. So, apparently, and you can actually still execute this using one adder, because you can actually multiplex this inputs, time division multiplexing of the inputs of this adder. Okay. So, that is one a possibility, but usually once you have this, you can actually rewrite this dependency into this, right. So, now you can see here instead of 4 cycle I can execute the things in another side, that there is a mistake here. So, the ACC will come here in 3 cycle, right. So, it was 4 cycle, this is 3 cycle. So, after doing this, although there is a loop carried dependencies, after unrolling I can actually restructure this dependency graph to improve the performance as well, right. So, if the basic idea is that if there is a loop carried dependency, unroll does not help much, right. So, that is the basic takeaway from this discussion, right. But if the loop is small and the loop there is no dependency among the operations or the iterations, operation into different iterations. So, then this unrolling gives you the maximum benefit. But as I shown in this example, that if there is a loop carried dependency, unrolling may not be that much helpful. Okay. So, I will now move to the middle path, what is called partial unrolling. Okay. So, the partial unrolling basically is a trade off between iterative execution versus complete unrolling, right. So, we have seen that the iterative execution is use minimum resource, maximum time, complete unrolling take minimum time, maximum resource, right. So, complete end. So, can I make a trade off between this? So, what is the trade off? Is the partial unroll. So, instead of complete unroll, you do the partial unroll. So, by a factor, right. So, you mention that if my loop is say running for 64 iterations, I make it factor 8. So, now my loop will iterate for 8 iterations, and consecutive 8 iterations operation will be executed in 1 iteration. Okay, that is the basic idea. So, it is decided by the unroll factor. So, you can give your unroll factor based on your requirement. Okay. So, let me take the same example, the accumulator example. So, I have 4 iterations, I just say ki unroll factor is 2, right. So, what I am doing is basically I want to do 2 iterations into 1 iteration, right. So, what I can do is basically I am doing this. So, accumulator is equal to D in, accumulator D in I plus 1, and I am incrementing I equal to I plus 1, here it is I plus plus, right. So, now this loop will iterate 2 times, because I reduce the number of iteration of the loop by a factor of 2. As a result, I unroll the loop by the unroll factor. Okay. So, this is how unrolling works, and you can understand that this is basically middle path, and based on your resource available you decide the unroll factor. If you have lot of resource available, you give a better the higher factor, then the number of iterations that will be running in parallel will be more, but if you have less resource, then you give the unroll factor less. Okay. So, that the number of operations to be running in parallel will be less, and you can utilize your resource, right. So, if you just take the same example, that accumulator, now I have 2 operations. So, this is the first operation where I am doing this ACC plus D in, and this is the output, and this is my D in I plus 1, and this is D in I. So, then the result is going there, right. So, I am now selecting, you can understand here that here in these operations ACC equal to ACC plus D in 0, right, and here then I am doing ACC equal to ACC plus D in 1. This is my I equal to 0 when I equal to 0, then my I will be 2, right. So, for when I equal to 2, what I am doing ACC equal to ACC plus D in 2 and then ACC equal to ACC plus D in 3, right, and I am done. So, for this input what I am going to select? I am going to select between this and this, because these are the things is going to added here, right. So, this is that is why I am selecting D in 0 and D in 2, right, and here for this second output this I plus 1 is 1 and 3, right. So, this is my 0. So, I D I. So, I plus 1 is basically D 1 and D 3. So, this is why this marks is selecting between 1 and 3 and this is my I plus 1. Okay. So, this is what try to show how we should multiplex the this arrays, and I am assuming this array is basically mapped to registers. Okay. They are all available in parallel. Okay. You can understand this partial unroll depends on your resource availability. You should decide your unroll factor and it will improve the performance, okay, without much increment of the resource requirement. Okay. So, if you take the same example of this and if you just make a factor equal to 2, you can understand that then the rewritten code will be like this: I equal to 0, I less than n, then I equal to I plus 2, right, and then here I am going to do AI equal to BI plus CI and then A I plus 1 equal to B I plus 1 plus C I plus 1, right. So, this is what the unroll factor equal to 2, right. So, if you just write here pragma in this code, if you just write pragma unroll factor 2, sorry, this factor equal to 2, unroll factor 2. So, it will automatically be converted internally like this, or you can write yourself. Okay. So, both is fine, and I am not drawing the diagram, but you can understand that you can use two operations to do this two things, right. So, this is AI, sorry, this is BI, this is CI, this is BI plus 1, this is CI plus 1, and this result is actually going to the A array. So, there are two data basically. So, this you write into I, this you write into I plus 1. So, this is how I should execute this, and you can understand that my rolled implementation will take 1, complete unroll will take say if it n equal to 4, it is 4 adder, and my partial unroll is taking 2. It is basically completely the middle one. Okay. So, that is what. So, one important point to be noted here is that with this unrolling, the access of array is getting increased. So, right. So, you can see here that earlier in this here every clock I am going to access one time A, one time B, one time C, right. So, now if this A, B and C are mapped to say block RAM, and then if I assume that this if I just doing the factor by 2, I can see now actually in every iteration I am accessing 2 value of A, 2 value of B, 2 value of C, right. So, if that particular block RAM is single port, then this will create a bottleneck, because you cannot access 2. So, this benefit you will not get, right. So, you have to still do it in sequence. So, if that particular block RAM is dual port, it is not a problem, because you can actually access 2 data, right. But if the unroll factor is 8, 10 or so on, right, in that case your dual port or single port does not help. So, how I can improve that? How can I make sure that even if I partially unroll and I am accessing more than 2 data of a particular array, I can actually achieve my required performance by doing the partitioning of the array. Okay. So, I will take a concrete example and I will show you how to do that. Okay. So, even if you take this example, so since suppose there is a single port array, okay. So, there are 2 accesses, and you can see that what is that data is getting access here, A 0, 2, 4, 6 and so on, right, and here I am going to access 1, 3, 5, 7 and so on. So, what I can do, I can actually split the array A into two arrays, right, array A to A1 and A2. Here I am going to put the data of 0, 2, 4, 6 and all those things, and here 1, 2, 1, 3, 5, 7 and those index data. So, now there are two arrays, these two arrays can be mapped to two different block RAM, and I can actually access those data because these are two different arrays. So, based on the access pattern, I have to decide how to partition the array into multiple arrays. So, the key takeaway or the key summary that I want to make from this slide is that just doing blindly unrolling, partial unrolling may not help, because your array increment, because loops are always come with arrays, and since the array access is increasing. So, if you assume that I am just doing unrolling, I will get the desired performance improvement, it will be bottlenecked by the array accesses. So, always once you apply this unroll, partial unroll, you have to make sure that you partition the array based on their access pattern, right. So, the example that I tried to show here, and if you just partition the array into that way, then only your improvement required performance benefit will be obtained, otherwise you will not get that. Okay. So, I take another good examples. So, suppose I have this code, right. So, this code you can see here there are two factors, one is channel and one is samples, right, and the total number of iterations is basically channel into samples. And what is happening here, you see carefully. So, basically what I am doing here, for every I just get the remainder value which is mod channel, right. So, the remainder value will be 0, 1 to 7, one of the values, right. And then what I am doing, corresponding that accumulator I am updating the adding the value D in. Okay. So, what is going to happen here? So, effectively, and then that value I am going to return out to D out. So, basically there are 8 channels, right. So, 8 channels and the corresponding data. So, whenever some I comes, and I am going to put that 0, 8, 16, 24 these datas, the corresponding D in value I am going to put into that ACC 0, the channel 0, this is my channel 0, right. Similarly, 1, 9, 17, 25, this index values I am going to add, I am going to put into channel 1, right. This is my ACC 1. You can understand this way. I have the 8th channel which is ACC 7, which will store 7, then 15, 23, 31 and so on, those corresponding inputs. Okay. So, this is how this code is working. Okay. So, you can understand here that there is a good chance, because this ACC there are 8 channel, right. So, there is a good chance that I can actually do a unroll of this loop by a unroll factor of 8, because these channels, so that I can actually parallelize this operation. This is my 1 iterations of 1 channel. So, basically 1 channel content, right. So, then this set of data will go into the channel, right. So, the same channel. So, what I can do, I can parallelize this. So, I can actually put a unroll factor 8, so that the iteration 1 to 7 will execute in one time in one iteration, 8 to 15 will be executed in the next iteration, 6 to 23 will be executed in next iteration and so on. Okay. So, this is what I can do. So, I am going to do that. So, I am going to do that I am going to put a unroll factor equal to 8 into this code, right. So, if we just do that, the tool automatically will rewrite this code into that way, right. So, basically you can understand that there will be 8 copy of this code, and this I plus 1, I plus 2, I plus 3, I plus 4 to I plus 7 will be used here, right. So, I am not writing that, but I hope you understand the corresponding loop body. Okay. But with this, what is the problem or the bottleneck I am getting here? You can see here that now, since I am going to execute this 8 copy of the body in same, so that D will be accessed, D in will be accessed 8 times now, and D out is also going to be used 8 times now. Earlier it was only 1. So, now whatever the way you map into D in into one block RAM, you cannot access all 8 data, right. So, you although you try to execute this one complete channel of execution in one iteration, you cannot achieve it because of this array access problem, right. So, now I have to split the array, and you can understand how you should split into the array. I can split the array into 8 copies, right, and such that this data I am going to put of D in into array 1, this data, that means index 0, 8, 16, 24 and so on, 32 and so on, this I am going to put in array 1, D in 1, D in 9, D in 17, D in 15, D in 33, this I am going to put say array 2 or D in 2 and so on. So, I am going to split this array or partition the array into 8 arrays, and partitioning is also very important, it is a cyclic manner, right. So, I am going to partition the array such that 0 goes to partition 1, 1 goes to partition 2, 2 goes to partition 3 and so on, right. So, this is how I am going to cyclic way I am going to partition. You cannot just partition blindly, then also it will not work. You have to see the access pattern and you have to make sure that the iterations that are now going to running in parallel, the corresponding data must be in the different arrays. They cannot be in the same array, then your performance improvement will not be achieved. Okay. So, if I just do that, so that is what can be done by this pragma, that you partition the array D in by a factor 8 and you partition the dimension 1, right. So, dimension 1 means it is only one dimension. So, you can actually do that. So, basically this way it will actually partition this way, and you can, this is actually important, is the cyclic. If you just write the cyclic, it will actually do that, 0 will be put in partition 1, 1, 2, partition 2 and so on, right. So, this is what I try to emphasize, that your Underl factor allow each channel to process in parallel, that 8 channel, every 8 sample, if only if the input and output array are also partitioned into cyclic manner to allow the multiple access per clock cycle. So, whatever I just explained, the same thing has to be done for D out as well, because D out is also going to access 8 times in one iteration. So, if you just do both unroll and partition, cyclic partition, then only you can actually run the 8 iterations of this loop in one cycle, right, and you can actually achieve the desired performance benefit. Okay. So, one more important small important factor, that sometime suppose I want to put a Underl factor which is not exactly divisible of this value. So, suppose this is my say 15 and I just put a Underl factor equal to 2. So, that means it is not that I am able to partition this particular iterations into evenly, right. So, because the 15 is not divisible by 2. So, but that is actually not a problem, because you can actually write this way, that you, because I want to put a Underl factor 2. So, I just put I equal to B I plus C I, and if I just put a line, if I plus is greater than, you just break it, otherwise you do this, and it is I plus 2, right. So, what is happening is, when I equal to 0, A 0 equal to B 0 plus C 0 going to happen, A 1 plus B 1 plus C 1 going to happen. When is I equal to 2, A 2 plus B 2 plus C 2 is going to happen, and this A 3 plus B 3 plus C 3 is going to happen. But when I equal to is 15, so only A 15 plus B 15 plus C 15 is going to happen, but this line will not be executed, because I am going to break it out from there. Okay. So, basically the takeaway from this particular slide is, so if you just put a Underl factor, you should not bother about whether it is exact divisible or not, because even if it is not, tool will make sure that you do not execute unnecessary things. Okay. It will stop unnecessary thing, but it is additional check. So, you try to factor it such a way that you should not have this kind of code, because whenever you add this code, it will always check, you should have a conditional checking, right, which will take some resource and time. But it does not stop you from factoring the loop. But if you try to do it in manually, this whole change, you have to physically add this kind of line, right. So, similarly, if you just try to do by factor 3 here, so you have to add a line like, if I plus 2 is greater than equal to n, then you break, right. Otherwise, you do A I plus 2 equal to B I plus 2 plus C I plus 2, right. So, basically after every operation, you have to check whether the I plus 1 or I plus 2 or I plus 3 is greater than equal to n, then you should break, otherwise you do the next operation. Okay. So, this is how you can actually manually do that, or if you do not do that, if you put Underl factor which is not perfectly multiple of this for the actual number of loop iteration, it will automatically do this in general, but it is not advisable to do that, because it actually take extra condition check in the hardware. Okay. So, with this I am going to summarize this class. So, I have seen that in this class that that loop, the 3 way of executing the loop. One is the complete unrolling, partially unrolling, or complete roll implementation, right. So, if you take this loop, this diagram summarize that. So, if you have a complete roll implementation, so you in iteration 1 you read a B3 C3 and then do the addition operation and then you write A3. So, this is your clock 1. In clock 2 you do read B2 C2, do the multiplication operation and write A2. So, this is your clock 2 and then clock 3 and clock 4, right. So, you need 4 clocks and I am assuming this. So, basically this is the iterations and you might need multiple clock cycle to do that, right. So, because your read might take some cycle. I am just saying that this is the operations and you have to schedule them also, right. But this is how the iterations works, right. But if you partially unroll say by 2, so read of 3 and 2 is going to happen, 2 multiplication is going to happen and 2 write to A3 and A2 is going to happen. And in the next iteration reading of B1 C1, B2 C0 and this 2 addition multiplication corresponding multiplication is going to happen and you are going to write A1 and A0 and you need basically 2 iterations. And if you completely unroll, everything is single cycle, right. So, all 4 reads from B and C, all 4 multiplications and all 4 write to A is going to happen in single iteration. And how many clock cycle is needed for these operations? It depends on your resource availability, right. So, it might 1 cycle or k cycle based on your resource availability and also how this arrays get mapped also, right. So, how this arrays goes mapped to block RAM also, it also is a deciding factor, because based on this access pattern you have to see, right. For example, here even if you do this and if you map this block RAM into this B and C into RAM, then you cannot access 4, right. You have to wait for 4 cycles, which is a single port. Even if you put into register, then you can access all them in parallel, right. So, this is what 2 factor depends and based on that your schedule time will be determined. Okay. So, with this I conclude this discussion. In the next class we are going to see how the loop will be pipelined in the hardware. Okay. Thank you.